Hello everyone, my name is Yuzhuo from Leuven, Belgium. The presentation title is Input Parallel Output Serial LLC Resonant Converter with Reconfigurable Output Voltage Outputs for 400 volts and 800 volt architecture in electric vehicle charging. The presentation is divided into the 4 parts. If you are interested in our work, please scan the QR codes with your mobile phone to download the full text of the paper, including the APEC papers and the one journal papers with more detail. As you know, the charging voltage for electric vehicle is transiting from 400 volts to 800 volts. This not only ensure higher charging power, but also shorten the charging times and improve charging efficiency. Besides charging voltage difference, there are also significant variation in charging power. This means the DC charging have 2 requirements, voltage capabilities and the power capability. Based on the input voltage type, the DC charging station can be divided into the AC input charging station and the DC input charging station. Both require DC-DC converter with a wide output voltage range and power and output power, which is also the focus of our work. Based on the state-of-the-art publication from the past 6 years, the typical method for achieving wide output voltage in DC-DC converters can categorize into several types: 2-stage conversion, module operations such as serial or parallel configurations, hybrid control, and multi-mode operation, also referred to as reconfigurable converters. To achieve power capabilities, module operation is the most common approach for increasing output power. Typical configuration include input parallel, and input serial, output parallel, as shown on the left. However, parameter mismatch among the modules remain a critical issue, directly leading to the voltage and the current imbalance, electrical and thermal overstress, and even thermal runaway. Many methods have been proposed to address balancing challenges, particularly for the resonant converters. This can be categorized into the loop-based active control, which require multiple sensors and feedback loops, and occasionally active switches, and the passive long-loop control, which relies on electrical or magnetic coupling, such as coupled inductor discussed in the following session. This section presents the proposed solution, a reconfigurable modular converter designed to achieve both wide output voltage range and high power outputs. The converter operates in 2 distinctive modes, tailored for 400 and 800 EV charging. In addition to featuring simplified control for soft switching and the soft switching capabilities, the proposed topology achieves automatic current sharing and voltage balance through a passive method based on coupled inductor. While the coupled inductor is not new, this will contribute a quantitatively designed methodology that specifically account for its impacts on the output voltage and the current balancing ratio. Detailed analysis is provided in the following session. There are 2 reconfigurable modes, no output charging and high output charging modes, which are controlled by the secondary side switch. When this switch is turned off, the operating principle is illustrated in the top right. The positive and the negative half cycles. Conversely, when the switch is closed, the converter enters the high output charging mode, where the output voltage is double compared to the no output charging modes. The corresponding current path of this configuration is provided. The the two resonant tongues behave differently across the two operating modes. These slides illustrate their equivalent circuit, taking the coupled inductor into account. However, directly analyze the voltage gains and the balance characteristic of this circuit remain challenging due to their coupling and the complex relationship. Therefore, a decoupling analysis for the coupled inductors is necessary. The slides present their corresponding decoupled equivalent circuit. Based on the decoupled equivalent circuit, the current sharing ratio can be derived. As illustrates, the Greek letter epsilon is employed to quantitatively evaluate the degree of current sharing between the two modules. In the worst case scenario, involve 10% mismatch in the resonant inductance and 5% mismatch in resonant capacitance. Common parameter tolerance. The figure on the right displays the normalized resonant currents. By setting a power imbalance threshold of less than 10%, we can calculate a minimum coupled inductance ratio of 7.59 is required to ensure stable operation. This flowchart illustrates a quantitatively design methodology which optimizes the trade-off between the wide output voltage range, system size, and efficiency. Further technical details and comprehensive analysis are available in this journal paper. Furthermore, the converter features automatic voltage balancing capabilities. As illustrated during the transition from low output charging to high output charging modes, operating at a switching frequency of 100 kHz and 62 kHz, respectively, the secondary side voltage VCD1 and VCD2 remain perfectly balanced. This balanced performance holds true when there is an initial voltage deviation. A similar balance effect is observed for CD13 and CD14, showing the robustness of the proposed converter. Following is experimental results. The table shows the parameter specification, and the picture on the right is the prototype. In the experimental verification part, the no output charging mode was first evaluated with a minimum output voltage of 200 volts. The two modules operate with an interleave operation, 180 degrees phase shift to reduce current ripple. The result demonstrates that the converter achieves excellent voltage and current sharing while maintaining zero voltage switching for all the switches. Moving to the 800 volts in high output charging modes, we can see the same level of performance. Even at the maximum voltage, the system remains perfectly balanced and continue to operate under full ZVS for the switches. In our first prototype, we employ higher inductance with a resonant frequency of 100 kHz. The peak efficiency reaches 93.7%, with an overall efficiency maintained above 92.1% across the whole output voltage range. In the secondary prototype, we increased the serial resonant frequency to 200 kHz and optimized the design, resulting in a significantly improved peak efficiency of 96.16%. This slide shows the dynamic waveform during the mode transition between low output voltage charging and the high output charging modes. Once the output voltage reaches the predefined threshold voltage, the mode transition is triggered. The experimental waveform demonstrates a seamless transition with a little overshoot, ensuring smooth and stable operation during reconfiguration. To sum up, the proposed module-level reconfigurable converter successfully achieved both voltage and power capability. It features an extensive output voltage range of 200 volts to 900 volts. It also simultaneously supports module operation for high power scaling. The system incorporates automatic balance through a passive coupled inductor method. Finally, the experimental prototype verified the design, achieving a peak efficiency of 96.16% of full soft switching. This slide shows the selective reference for this presentation. That's all. Thank you. If you have any comments, feedbacks, or interest in this paper, please directly contact me by my emails. That's all.